Okay, so the next thing we're going to discuss is error analysis. And error analysis can be broken up into two categories. So when you're looking at the error analysis of one-step methods, right, this is sort of concerned with two classes. So the first one is this idea of local error. And so essentially the local error is the error you make if you have the same initial conditions and the same time step, and you apply one step of your one-step method versus the exact time h flow of the flow map. Okay? And of course the problem with the flow map is that you typically don't have the explicit expression for it, because of course if you did, then you should just stop. There's no need to approximate stuff. You have the exact solution. You should move on. So what you have to do then in practice is you replace the exact flow map with basically a Taylor approximation. So what you do is you compare the Taylor series of the true solution right with the one-step method. Okay, and then the other thing that one cares about is this idea of global error. And global error is what happens when you accumulate this error over the entire trajectory. So the accumulated error over the computation of the trajectory. And where this gets complicated, of course, is that even though initially you have the right initial conditions, after taking one step, there is an error which comes on the local error. And so henceforth, you are applying the one-step method, it's like to an initial condition, which is in some sense incorrect. Okay, and so there is potentially an amplification of that error together with the new error at every step from the local error. And so when you analyze the global error of a numerical method, there are these two sources of errors, it's like which feed into it. Okay, so it's perhaps helpful to draw a picture of what we mean by that, right? So you start off with an initial condition z0, which is going to be consistent with both the exacts, or it's going to be applied to both the exact time h flow and one-step method. So imagine z0 is part of some solution curve like the following. All right. So after a certain time, right, this would be if you will, the exact flow map applied to z0. Okay, so this is the exact solution, and maybe there's a numerical approximation to it, which I call z1, which is the numerical flow or numerical one-step method applied to z0. Okay, so immediately, and this difference here is what we call the local error. All right. And of course, once you have that, you have to apply again another application of the one-step method. So you can ask whether there is there's another exact solution which goes through the point z1. Okay, and all right. So this is what you get if you apply the exact solution map to z1. This maybe is what you get if you apply the numerical method to Z1. Okay, and then the error you're really trying to compute, if you will, is the difference between the exact solution, okay, with the numerical solution. Okay, and what you're going to do is you're going to try to apply to use the triangle inequality to estimate this error by breaking it up into two parts, one of which is the error between the numerical solution and the exact time h flow applied to now the Z1 data. Okay, so this is of course nothing more than a local error term. And in addition to that, you're now looking at the difference of the errors or difference between two exact trajectories, but with different initial conditions. Okay, so this is something which you can bound by using what is known as the Lipschitz constant of the vector field. So there will be, and more or less that is going to measure the extent to which nearby trajectories diverge from each other by the exact flow. So we're going to use these two pieces of information to then construct the global error analysis. Okay, so that's sort of the picture to keep in mind. But again, let's start with the local error. So the local error is the difference between the exact and approximate solution for a time step h starting at the point, let's call that z bar. Okay. So what you're looking at is the difference between the numerical one-step method with a time step h applied to z bar, right, and the exact flow map, again with a time step h applied to z bar. Okay, and so this is what we call the local error with time step h at the point z bar. Okay, and of course, in general, we don't know what this exact flow map is, and so what we're going to do is we're going to do a Taylor expansion of the flow map. So use a Taylor expansion of the exact flow map. Okay, and then what will end up happening is that this local error term is going to look at like some sort of series in H. Okay, so it's going to be some CP plus 1, which depends on the initial condition z bar up to some power h to the p plus 1 plus higher order terms. Okay, and we call this p, which is the sort of, well, p plus 1 is the exponent of the leading order error term. We call that p the order of the method. Okay, so this p is the order of the method. So you might ask, why is the order of method p when the error term is big O of p plus 1? And that's because this is just the local error term. And what you're going to end up finding is that if you have a local error which looks like big O of h to the p plus 1, then the global error is going to be big O of h to the p. And so this p here measures the the rate at which the global error decays. It's like as you let the time step go to 0. And so that, of course, is what you really care about. You don't care about what the error is when you just take one step of the method. You care what the error is when you've integrated it up to the time whose solution you're looking for. All right. So let's look at the local error for a bunch of these elementary one-step methods. Okay, so with the Euler method, you can check that the local error is of the form minus 1/2 z double dot h squared plus big O of h cubed. Okay, so this is telling you that the p in this is 1. And that says that the Euler method is a first order accurate method, which means that the global error converges linearly. It's like in the time step h. All right, and with implicit Euler, the local error is of the form 1/2 z double dot h squared plus big O of h cubed. The trapezoidal rule is local error hz, okay, which is minus, well, actually, it's just sorry, 1/12 the third derivative of z, okay, h cubed plus big O of h to the 4. And implicit midpoint has the local error of the form 1/12 z cubed h cubed big O of h to the 4 as well. Okay, so so both trapezoidal rule and implicit midpoint have the same local error. Okay, at least to leading order. So, so from this, you can see that the Euler method and the implicit Euler method are first order methods, and the trapezoidal rule and implicit midpoint rule are second order. So Euler and implicit Euler are first order. Methods, and trapezoidal and implicit midpoint are second order methods. Okay. All right. So again, if you want to analyze the global error, what you're going to find basically is that there is a recurrence relationship, if you will. And what happens is that every time you take a step, there is this local error term, but there is an amplification of the error from the previous step, because what happens is that you are using the incorrect initial data, if you will, for that step. And that error in the initial data is exactly what the error was at the previous time. Okay, so there's going to be a linear there's going to be an amplification at every step of the error, as well as the introduction of new local error. So if you want to do the error analysis, it's oftentimes helpful to prove a lemma, which is known as the Discrete Gronwall lemma. So that's what I will talk about now. So this is related to the idea of convergence of one-step methods. Okay, there's a lemma. Okay, so let's say you have a positive sequence. Let's call that Zn. Okay, n goes from 0 to big N, and it satisfies the following relationship. So Zn plus 1 is less than equal to some amplification of Z at the previous point plus some additional error. So what's going to happen, it's like when you apply this to the error analysis of a one-step method, is that B is going to be your local error term. Z is going to be the error at the nth step of the method, and then A is some amplification factor. Okay, so that's what's going to happen, and we're going to first it's like establish a result about what given a error which satisfies this kind of inequality, what you can then say about the error at a global level. Okay, so you want this to be true for constants. Let's say a greater than 0 and some b. Okay, then what happens is that Zn is less than equal to b over a minus 1, a to the n minus 1 plus a to the n z0. And this is for the case where a is not equal to 1. And then, and if a is equal to 1, then it's a lot easier. Zn is less than equal to n times b plus z0. This is for a equals to 1. Okay. So the a equals to 1 case is relatively straightforward, so I'm going to omit that. Okay, so so you can prove this by induction. You can prove the a equals to 1 case by induction quite easily. Okay, so I'm going to omit this. So I'm going to consider the a not equal to 1 case. Okay, so let's say you have n equals to 0, then this inequality reduces to the following. So that's saying that z0 is less than equal to b over a minus 1, a to the 0 minus 1, right, plus a to the 0 z0. But of course, a to the 0 is 1, 1 minus 1 is 0, so this first term vanishes and you're left with just 1 times z0, so that's just z0. So the first condition is saying that z0 is less than or equal to z0, which obviously is satisfied. Okay, so this holds. So let's then do the inductive step. Okay, so you assume this is true for n equals to k, and then you want to show that's true for n equals to k plus 1. All right? So you know that zk plus 1, right, which is the next step, is less than equal to, it satisfies this relationship, azk plus b. All right? And we also know that the zk satisfies this kind of inequality. So let's just substitute that. So this is less than equal to a, b over a minus 1, a to the k minus 1, plus a to the k plus 1, z0 plus b. All right, and then you can rewrite this in the form you want, which is that b over a minus 1, a to the k plus 1 minus 1 plus a to the k plus 1 z0. Okay, and again, that's because, yeah, so you can basically just multiply this throughout, and there is this term which you have to deal with, and that's going to cancel out the b term. Okay. All right, so in any case, it's like zk plus 1 satisfies the inequality which you want for the n equals to k plus 1 case, so you're done. So you proved the inequality by induction. Okay, so now we're going to use this to prove that the Euler method converges. And in order to do that, you have to introduce this idea of Lipschitz continuity of the vector field. Okay, so let F be Lipschitz continuous. Vector field. All right, so what that means is that if you evaluate F at two different points, then the difference in some appropriate norm is bounded by some multiple L of the difference between the 2 points, if you will. Okay, so where L greater than 0 is the Lipschitz constant. All right, so if you have this vector field which satisfies this Lipschitz continuity condition, then you can talk about the whether a numerical one-step method is convergent. So a method is convergent, right, if for every such vector field, you have the following property, right? And you have to give me a time t, okay? Then you can look at the error, if you will, between the numerical solution, Zn, okay, and the exact solution, Z at Tn. And I want to take the max error you're making, so this is like a little L infinity error, okay? So over the entire discrete trajectory where the numerical solution is defined, I want to make sure that the error between that and the exact solution, right, I want to measure the maximum error you make. And then I would like that the limit as the time step going to 0 with the property that the time step is equal to the total time divided by n, which is the number of steps. All right, so what you have to do basically is that as h goes to 0, the number of steps has to go to infinity. But in that limit, this maximum pointwise error you make, right, goes to 0. Okay, so this is what we mean when we say a numerical method is convergent. All right, and this is, if you will, the error at the nth step. So you can also take n going to infinity. You can also let n go to infinity, right? Where h is basically the total time divided by n. So either of those limits work for you. Okay, so they're equivalent. All right, so in any case, so now what we'd like to do is that if the differential equation, it's like has a vector field which satisfies this Lipschitz continuity condition, then we want to check that the Euler method is convergent in this sense here. Okay, and we're going to do this by basically doing a global error analysis which leverages this discrete Gronwall lemma which we proved. Okay, so the theorem is that the Euler method is convergent. Okay, so how do I go about doing this? So let's try proving this. All right, so you can apply Taylor's theorem. So Taylor's theorem tells you that the solution at the new time is equal to the solution at the old time plus h times f evaluated at the sort of the old solution, it's like plus something which is big O of h squared. Okay, and you know that Euler's method gives this kind of update that Zn plus 1 is equal to Zn plus hf at Zn. Okay, so those are the things you're going to be asked to compare. You're going to compare the numerical solutions generated by the Euler method with the exact solution which satisfies this kind of Taylor expansion. All right, so I'm going to write down the error, En plus 1. So En plus 1 is the solution at the n plus first point. So this is Zn plus 1 minus Z at time Tn plus 1. Okay. All right. So you can then substitute these expressions. And so, you know, the Zn plus 1 involves a Zn plus stuff, and the Z at time Tn plus 1 involves a Z at Tn. So part of this term, it's like becomes the error at the end stage, and then the other part has to do with the difference of two vector fields which are evaluated at different points, plus some higher order error term. Okay, so it's En plus h times f evaluated at Zn, okay, minus f evaluated at Z Tn, plus something which is big O of h squared. Okay, so Zn, okay, can be related to Z at Tn. So Zn is Z at Tn plus the error at the end stage, right? Just by definition. Okay, so what you can do then is that you can use you can estimate this term here, which is the difference of the vector field evaluated at two different points, where the 2 points differ by the error term. Okay, you can estimate this error term here by the sort of the Lipschitz inequality, and then you can apply the triangle inequality here. Okay, so the Lipschitz condition plus triangle inequality give you the following, right? That's the norm of the error at the n plus first stage, right, is less than equal to the norm of the error at the end stage, right, plus h times the Lipschitz constant applied, multiplied by the norm between the difference of the 2 points, but we already said that the difference of the 2 points is just measured by En, so there's an En term here, right, plus some constant C h squared, which is modeling this big O of h squared error term here. So what you end up getting then, I can combine these two terms. This is equal to 1 plus HL times the error at the end stage, right, plus C h squared. All right, so now we're exactly in the form which we want. It's like this is the form which we had in the discrete Gronwall lemma. The, you know, the error, the global error, it's like at the new time is equal to some multiple of the global error at the previous time plus some constant term. Okay, so now you can apply the discrete Gronwall inequality. All right, so the discrete Gronwall inequality gives the following, okay, that the error at the nth stage is less than equal to CH squared over kappa minus 1, okay, kappa to the nth power of minus 1 plus kappa to the n, the error at the 0th step. And the observation is that the error at the 0th step is 0 because when you start off this method, you apply the one-step method and the exact time h flow map to the same initial data. So the error at the 0 stage is 0, so this vanishes. Okay, and then where kappa is equal to 1 plus h times the Lipschitz constant. Okay, so with that, it's like you get that the error at the end stage is less than equal to ch squared over kappa minus 1, right? I can put back the 1 plus hl term. Actually, let me sort of do that for both of these. So I'm going to put back, it's like what kappa is. Okay, so you get ch squared over hl, okay, 1 plus hl to the nth power minus 1. Okay, and then h cancels, so you just get ch over l. So this is ch over l, again, 1 plus hl to the nth power minus 1. So you can observe that h times l is greater than 0. So in particular, if you look at this thing, it's like you can relate it to the exponential. So so you have 1 plus hl. So because hl is greater than 0, 1 plus hl is bounded from above by the exponential of h times l. Okay, so what I'm going to do is I'm going to replace this 1 plus hl to the nth power by e to the hln. Okay, so this implies that the error at the nth stage is less than equal to ch over l, okay, ehln, okay, minus 1. All right, and so you know that you can bound this from above because h times capital N, which is the maximum little n you can take, is bounded from above by t. So this is less than equal to chl e to the tl minus 1. Okay, so now you can ask, well, what happens as h goes to 0? This is just a constant which depends only on the Lipschitz constant and the time of the final time, if you will, which you're integrating up to. And so the only dependence on h is up in front, and it depends linearly in h. So you can conclude that that as h goes to 0, right, that the error, it's like at every point, right, goes to 0. So the limit as h goes to 0 of this error is 0, and as a consequence, the Euler method is convergent. All right. So that's basically, again, a proof that the method converges. And what we'll see later on is that there are other ways of proving convergence, but this is a fairly direct way of proving convergence of a relatively simple method.